Well, good morning. And today we are going to continue our discussion of Fourier transforms and Fourier series. So let's just quickly review what we did from last time. So you remember for Fourier series, we basically we saw that any periodic waveform could be expressed as in Fourier series. And there were two different ways to write it. One was the more classical form of writing it in terms of sines and cosines. So writing x of t as the sum of coefficients a n's and from negative 0 to plus infinity times cosine of n omega naught t plus b n sine of n omega naught t. And alternatively, we saw that you could actually write this as a sum of exponentials, because we know that we can write sines and cosines as sums of exponentials, complex exponentials. So we could also write this as sum of from negative infinity to positive infinity of n, Cn e to the j omega 0 n omega 0 and t, which you could also write as sum of n from negative infinity to positive infinity of Cn e to the j 2 pi n f naught t, if you replace omega naught with knowing that omega naught is really 2 pi f naught. So this is the frequency and this is the angular frequency. And then we also saw how you could calculate these coefficients, right? So an and bn's, an was 2 over t, integral from negative t over 2 to t over 2 of x of t cosine of n omega 0 t dt. And similarly, bn was, and this is all true except for an for all n's other than 0. So a0 would be 1 over t, integral from negative 1 over t, negative t over 2 to t over 2 of x of t dt, which is the average of the signal. And then bn was the similar integral 2 over t from negative t over t to t over 2 or to t over 2, which basically means over one period, sine x of t times sine of n omega naught t dt. And from these, we also calculated that Cn, the Cn which basically became integral 1 over t integral from negative t over 2 to t over 2 of x of t times e to the j 2 pi f naught t, or j, you could write it as j omega naught t dt, which is also equal to 1 over t integral from negative t over 2 to t over 2 of x of t e to the j 2 pi n f naught t dt. So you're essentially what you're doing, you're really doing an inner product. If you want to think it a little bit more advanced, this is a linear algebra is essentially a vector space, and these are the bases vectors, the cosines and sines, or exponentials. And there was also a relationship between these two. So in this case, by the way, the Cn's, if for real x of t, Cn's complex conjugates was C negative n. So basically, the Cn and C minus n were complex conjugates of each other. And there was also a relationship between these things. So Cn, I think, was an minus jbn over 2. And that's why this 2 appears there, but not there. Yes?
Shouldn't there be a minus n in the exponents for Cn and for Cn?
No.
Okay.
No. For the exponent? No, I think it's okay. Yeah, this is positive. Yeah, so this definition is positive, essentially, right? It's a definition. So this is okay, right?
I meant at the very bottom.
Oh, here?
Because, like, don't you have Hermitian symmetry? So, like,
Yeah, okay, yeah, no, here you have a minus n, yes, that's. But that doesn't really get into the rest of our conversation, but yeah, that's right. So now, what does this mean? It means that essentially you could think about a periodic waveform as a bunch of sines and cosines. And it's a useful thing, very useful because you can do a lot of interesting things with it. But now you can even generalize it a little bit further. You can think about this as, so what we did next was to say, look, okay, so we have this, and then we could write a 6, so we can write an x of t based on this. So basically I'm just copying here. X of t is Cn, a sum of, it up a little bit here. So it would be the sum for n from negative infinity to positive infinity of Cn e to the j n. You can write as 2 pi n f naught t. And you could write this as you could say, okay, well, that's fine, but I also can use the sifting property of the delta. So I can write this as noting the fact that e to the j 2 pi n f naught j 2 pi n f naught t can be written as this integral from this very basic property of delta that we discussed very early on in the class as e to the j 2 pi ft delta of f minus nf naught df. Yes?
So over there, where did the 2 over t go?
When you went to one of the c?
When it went from 2 over t to 1 over t.
No. So that's for Cn. So that this, because this is the relationship between Cn. So the question is, where did the 2 go here?
In the a naught.
A naught is a special case. Okay. In this, when you want to write it in sines and cosines.
Okay, so
A naught for just for the DC part, because think about it, this is the average, right? So it should be 1 over t. The rest of them are 2 over t. When you write it in this form, then that disappears. That's why this is the preferred form.
So a naught is like an is only for.
An is for all n not equals.
Okay.
Yeah, good. So this is valid for all n's, not equals 0. Yes. So now going back to this, so what we have here is that so now we can actually plug this expression back in and see what happens. So when we do that, we say x of t is now, I can plug it into that integral, into that sum. And what I can also, since we did this before, and I can switch the order of summation and integration. So when I order to change the order of summation and integration, this is what I'm going to end up with. So I'll keep the associated differential next to my integral to avoid confusion. Delta of f minus nf naught. These are the parameters that are not functions of n. Well, this one is. Sorry. This one isn't. Exponential is not a function of n. So I can take it out of the sum. And then what is left is going to be a function of n, which is going to be Cn delta of f minus nf naught. And what we did is that we said, okay, look, this whole thing, we called it x of f, capital X of f. And we called this, and we'll see this is just the Fourier transform. But what does this represent? What's the meaning of this thing? Let's look at it a little bit more carefully to see what that means to us. So let me write it in that form first. So x of t is integral from negative infinity to positive infinity of capital X of f e to the j 2 pi ft df. And here, so basically, that's what it is. Now, let's look at this for example. So far we are talking about a periodic. So far still, the way we've written it is a periodic waveform, right? So what does this look like? What does this circled object look like? It's a function of frequency, obviously, right? And it's a bunch of impulses. So if you look at it and plot it versus f, so this is the way it looks like. So you have, this is the origin. So it has a bunch of impulses scaled by Cn's. So if you look at, and considering the fact that Cn's and C negative n's are complex conjugates, so I would just if this is the magnitude part of it, shown, this should look symmetrical. Should keep going on. So you have a bunch of impulses, C0, scaled by C0, C1, C2, C3, C4, negative, C negative 1, C negative 2, C negative 3, and so on and so forth. So this is what X, capital X of F looks like. And the spacing of these things, so this is happening at F0, 2F0, 3F0, and so on and so forth. So negative F0, so this spacing is F0. Yes?
Is that just the real part of it?
Well, yeah, it's a magnitude really I'm showing. What I'm showing is magnitude, but I'm going to keep it this way a little bit. I'm going to play fast and loose with it a little bit now, for now, just because we want to kind of develop a little bit of intuition. But yes, this is really, I mean, for this to make sense, it should be the magnitude of this thing, because it's a complex quantity now. But forget about that for a second. So what does this represent? What does this picture represent, this X of F? It shows how much energy you have at different frequencies, right? If you think about it. So it's, for example, in this picture, it says that you have more energy at lower frequencies, and the frequency increases. At higher frequencies, you have less and less energy. So this is really the spectrum, what they call the spectrum of the signal. If you think about the spectrum of light, that also represents, you know, how much, it's a breakdown of how much energy you have at different frequencies or different wavelengths. So this is the spectrum of the signal. It's actually called the spectrum. Now, this is still for a periodic waveform, right? Because, and we know F0 is 1 over t, the period of the waveform. So now, as we talked about it before, so how do you deal with things that are aperiodic, that are not periodic? You can think about them as being periodic with an very large period, right? As the period goes to infinity. And again, you can make the argument that, even, the entire life of universe could be the period, and then you can make it repetitive, and then you get whatever you want. So as you increase the period, what happened to F0? What happens to F0? So obviously it becomes smaller, right? So what happens to this plot as you have something with longer and longer period? These impulses start getting closer and closer to each other, right? So in the limit, in the limit of t going to infinity, is going to turn into a continuous function. Which is going to be what we call the Fourier transform, or the spectrum of the signal. So this is a continuous. So what happens is that if the signal, to begin with, was not periodic, if it was aperiodic, instead of getting a whole bunch of impulses, you get a continuous signal at the output, which still represents how much energy you have within each limited band. So if you pick, let's say, a narrow bandwidth here, or df, or delta f, you can basically see how much energy you have within that. I mean, you have to do it two-sided because this is also part of that. But that's where what it shows you. It's not exactly the power of spectral density yet, because power of spectral density is defined slightly differently. But it's very related to it. Actually, becomes the power of spectral density of a deterministic signal. But the power of spectral density, as you will see later on, it allows you to deal with stochastic random signals and define power spectrum for the random signal. And as you will see later on, it's really the Fourier transform of the autocorrelation of the signal, not the Fourier transform of the signal itself. Because when you're dealing with random signals, you're looking at different, each sample may be different. But again, that's outside the scope. That's like 1/16 stuff that you will extensively discuss and review. But anyway, so that was this concept of spectrum, right? And that led us to, so now if you look at this expression, and I'm going to rewrite it here. So it says that's a way of constructing the signal from this capital X of f, right? So you can write it as, you can say x of t, you can construct it as that. And I'll show it as inverse Fourier transform of x of f, where inverse Fourier transform is defined as x of f e to the j 2 pi ft df. Now, if this is the inverse Fourier transform, what is the Fourier transform itself? Well, the Fourier transform, for a second I posit this, and we'll see why it is several different ways, really, is going to be the same thing with a minus sign difference. So it's the same operation. So it's integral from negative infinity to positive infinity of x of t e to the negative j2 pi ft dt. So this is what we call the Fourier transform. So this is the Fourier transform, and this is the inverse Fourier transform. Yes?
For finite Fourier transform, do we have to multiply by a factor, kind of like how we did when we considered like one case of the summation in the Fourier series? Or do we just change the interval bounds to be like to the 2 times?
What do you mean by finite Fourier transform?
So like if we have like a waveform, we're considering only like so like if we have a cosine function, we're only considering like the first period of it.
So you have to be careful. So you said you're talking about, you said if you have a cosine function. If you have a cosine function, if you're doing a Fourier transform, you have to really consider the entire function from negative infinity to positive. That's the definition of Fourier transform, if you will. Now, Fourier transform of different signals are different. So for example, you can have a one-sided signal. So if you're taking Fourier transform of cosine of omega 0 t, that would be different from Fourier transform of cosine of omega 0 t times u of t. They're two different functions, so they have two different Fourier. But in either case, the definition of Fourier transform is this. The integral goes from negative infinity to positive infinity. Now, this function may be 0 may be 0 at negative infinity and positive infinity. It may be non-zero only for a finite period of time. What it does, it just changes the limits of integration when you calculate that integral. But it's an artifact of this function not being 0 outside the range. It doesn't change the definition. The definition is still exactly the same. It's just a question of what function it is that you're integrating. Some of them have values all the way from negative infinity to positive infinity. Some of them have values over limited range. And therefore, your integration, the task of integration becomes easier, presumably, or different, if not easier. All right. Any other questions? Yes?
So like the same way we have like operator lookup tables,
Mhm.
we'd be able to use like lookup tables for like
Yeah.
common Fourier transforms?
Yes. So the question is that can we use similar lookup tables as for operators for Fourier transform? And you should kind of already know the answer, because if you look at this carefully, you will see that this is just Laplace transform. What was Laplace transform of x of t? Was integral from negative infinity to positive infinity x of t e to the negative st dt. But now, if you look at it, you will see that Fourier transform of x of t would be, so if we show it as x of f, is Laplace transform of j2 pi f, or j omega. Right? Because if you just plug in j omega, set s to j omega, s equals j omega, or j2 pi f. Into this, you will see that it becomes exactly this expression. So Fourier transform is a special case of Laplace transform when it's evaluated only on the j omega axis, only on the imaginary axis. So it's a special case. Now, and therefore you can use everything that you had for Laplace transform. All of those are applicable. So those lookup tables are essentially, which were the similar ones as the ones that you had for operator. Not exactly the same, but similar. Now, because of that, and you may ask, then if it's a special case, why are we bothering with it? Because we already had the Laplace transform, which was the more general case, then why bother with this special case now? Why bother with the special case? Why? The answer is on this whiteboard, but why? Yes?
Because when you evaluate on the j omega axis, some things don't converge.
So when you evaluate it on the j omega axis, some things don't converge? If that were, okay, so if that's true, then that would not be an advantage, right? So, no, I mean, there's something that's happening here that you cannot do with the Laplace transform. Yes? It has an inverse. That's well defined. I mean, Laplace transform has an inverse, but it's not something that you want to calculate. It's like the solution for the fourth order equation or something like that. it's not fun. It's possible to find it, but it's not very useful. But now the beauty of this thing is that its inverse, it's essentially the same function with a minus sign, same operation. So Fourier transform, you could say Fourier transform is its own inverse, quote unquote, modular a minus sign. Right? Yes?
I seem to recall there's like a breakdown for the relation between Laplace transform and the Fourier transform for U of t. Could you go over that?
Yes. So again, it's all of these things that happen. There are some singularities that you have to deal with. We'll go over that at some level. But yes, there are some. Again, this analogy is kind of conceptual. But if you want to get into the nitty-gritty of it, because you're on the j omega axis, some interesting things happen. But the beauty of this thing is that actually it gives you a lot more useful information. And you can do a lot more with Fourier transform because of this inverse. So you can go back and forth between the frequency domain and time domain. You know, we've been kind of like dancing around and beating around this bush of frequency domain, time domain stuff. And now we are really facing it head on. This allows you to kind of like think about this duality of frequency and time. And it's really duality you will see. And there are a lot of interesting things there that are happening. And really by doing it this way, you can get to that. So let's just do a couple of interesting things here. So one important thing is that I just posited this, right? I didn't really prove that this is the inverse of that. Can we see if it's inverse of that or not? Let's see. Well, it shouldn't be that difficult to verify, right? Because if x of t is written like that, what if I plug this back into this guy, this integral, and put it in here, and see if I can recover x of t? That would show that it's the inverse, right? So let's do that. So I'm going to take this, x of f, and then plug this thing in there. So what I'm going to write is this integral first, e to the j 2 pi ft. Now I'm going to plug x of f from here. So then there's a second integral, negative j 2 pi f. Let's call this tau d tau. Oh, no, this should be d tau x of tau. Right? So I'm plugging this back into this to verify that this is actually inverse function, inverse Fourier transform is the inverse. So, well, okay, what do I do with this? So let's see. As usual, usually when you have these two integrals, you put one inside the other, you want to switch the order and see what happens. Right? So you swap these two integrals. So I get integral from negative infinity to positive infinity of d tau. And then this is a function of both t and tau. This is a both function of t and tau. They remain there, so I get x of tau. And then what's left here is integral from negative infinity to positive infinity of the product of these two, right? Which gives me e to the j 2 pi f t minus tau into df. Is everyone okay with what I've done so far? I just swapped the two integrals. Swap the order. That's what I did. So I brought this integral out and put this in. So that's what I get. I took the things that were not functions of f out of this integral and put them up front inside the outer integral, if you will. There's the inner integral and outer integral. So this is the inner integral. So now you have to calculate this integral. Now, what is this integral? Let me present something simpler to you for a second as a kind of a side note. What is the integral from negative infinity to positive infinity of e to the j 2 pi ft df? What is this integral? Does anyone have an idea? This integral actually is interesting, very interesting thing. Yes? Sinc?
Yes.
Yeah. Well, not yes. It's a limit of a sinc. We'll see what it is. So let's do the integral. How do we calculate this? So one way to calculate this is to write this as limit of a going to infinity of integral from negative a to positive a e to the j 2 pi ft df, right? So now what is that? How do we integrate? So let's find that integral first. So this is equal to limits of a going to infinity of this. So what is this integral? Can we calculate this integral? That shouldn't be that bad, right? It's an exponential. So we say it's 1 over j 2 pi t, which is all the coefficients other than f of the argument. And then this function, it's the exponential evaluated at this value minus evaluated at this value, right? So which would be e to the j 2 pi at minus e to the negative j 2 pi at. So do you see a familiar form here? Something we can work with. If I take this 2j with the rest of this, what is that? Sine, right? So this becomes limit of a going to infinity of 1 over pi t sine of 2 pi a t. Right? Which I can rewrite slightly differently. I can write this as a going to infinity. I can multiply and divide by an a and a 2. So I get 2a over pi t, and then write it as sine of 2 pi at over 2 pi at. Now, this is, so this is called, we call this a sinc. So let me write this here. So we define sinc here as sinc of x is sine of x over x. Now, to make matters confusing for you, there are two different definitions of sinc. One is that, and one is when you calculate this as sine of pi x over pi x. Now, depending on who you talk to, they have two different definitions of sinc. By the way, sinc stands for sine cardinal. So C stands for cardinal. But anyway, and so sinc really, with the way we define it, it's not even that. So sinc of x, we define it as sine of x over x when x is not equal to 0, and then as 1 when x equals to 0. Now, the way you define it this way is it makes it a continuous function because the limit of this at x equals 0 when x goes to 0 is 1. So it sets it to its limit, although it's not defined at x equals 0. Yes?
How did we end up with 2 pi's and 2 t's in the denominator?
I just multiplied it by 2a and divided by 2a.
But then we have divided by pi squared t squared.
Oh, no, okay, sorry. Yes, this is incorrect. Yes, thank you. So this is just, it's just 2a. Thank you. Yeah. Are you happy? Yeah. Well, I'm happy too. Good. So now, yes, thank you for that correction. It's 2a, just a 2a. So, but anyway, so this is the sinc. So now some people define sinc as sinc sine of pi x over pi x. So you have to look at which definition they're using. So in this, here we use just a basic definition. Anyway, so it is that limit, right? What does that look like? So let's look at it for a second. If you look at this waveform, a sinc function looks like this. It's a sine, right, over x, sine of x over x. But at this point, what is this value? So this whole thing becomes 1 by definition at 1, at 0. So this becomes, the height is 2a. What is this first crossing here, or first 0 crossing? When sine goes to 0, right? Which happens at what? The first time it goes to 0 after 0. At pi. So this point is where this becomes pi, basically when 2at is 1, or in other words, when t is 1 over 2a. So this width is a. So as you in the limit, look at what happens. In the limit, it gets narrower and narrower, right? That middle lobe becomes narrower and narrower and taller and taller. It should remind you of something. What is the thing? There, yes. The width is 1 over a, yes, thank you. Yes. Yes, the width is 1 over a, yes, thank you. Because that's 2 over a, obviously, this is 1 over a, thank you. So the width is 1 over a, and the height is 2a. So it kind of looks like the impulse in the sense that in the limit, right, it should be 0 at all other times except for 0, and at 0 it goes to infinity. But it doesn't necessarily make it an impulse. That by itself doesn't make it an impulse. Impulse has a very specific property, right? So we have to show that it has that specific property. What was that specific property? There are lots of functions that go to very large values at 0 and are 0 at other times, but they are not impulse, Dirac deltas. Dirac delta has that one extra property. The area is 1. Right? So the question is the area of this thing 1? Well, what is the area of this thing? Think about this. Well, what is the integral of this function? So to determine the area of that thing, we have to look at the integral of this thing, right? From negative infinity to positive infinity of sine of 2 pi at over 2 pi at dt. So if I calculate that integral, what is that? Well, I can do a change of variable and write this as, define this as d tau, or tau, where tau is 2 pi at. If I do that, then I have to write it as sine of tau over tau, integral from negative infinity to positive infinity, and scale it by 2a pi. So that integral is this integral. Now, does anyone know what the integral of sine of x over x dx from negative infinity to positive infinity is? It's pi. You can do it with contour integrals, essentially. So it is pi. And you can see that that pi cancels this pi. This 2a then cancels this 2a. And you are left with this integral being 1. And that proves that this thing is delta of t. So now it's interesting. Integral of e to the j 2 pi ft from negative infinity to positive infinity df is delta of t. Kind of an interesting result, right? Yeah. So now, having done this side, let's come back to our proof of Fourier transform when it's inverse. So now, knowing that, what is this integral? What is this inner integral? Okay. What is that? What is this integral? Now, based on what we've learned here, that this integral is delta of t, what is this integral? Delta of t minus tau, right? That's the new variable, right? So now I can replace that with delta of t minus tau. So I get negative infinity to positive infinity x of tau, delta of t minus tau d tau. Now what is this integral? Think about it. Delta of t, this is the shifting integral, right? Delta of t is 0 at all time except for t equal tau. So it's only the value of x of t tau at t that matters. So it pulls that out. So it becomes x of t. I mean, if you want to do it formally, you have to do one more step. It becomes x of t integral of delta of t minus tau dt, d tau, sorry, which basically is 1. So this becomes x of t. Right? So you can see that we started with x of t, and applying the Fourier transform and its inverse, we got back to the x of t, which shows that these two transforms are indeed inverses of each other. So any questions? Yes,
So
Daniel.
you mentioned that we could similarly use a lookup table for this. The book, when it introduces this, it gives us an example that's like very common, like e to the t. And it's like now intuitively you might think, oh, because of like prior things, that means that this is 1 over j omega, like minus a or whatnot.
Yeah, right.
And then it goes on.
Right, correct. So.
Gotcha. No, it's
Right. Yes. No. So that's why there are special cases for lookup table. Yes. So you're making a good point in the sense that you need to be careful when you're on the j omega axis. But the point of doing it this way, the way I'm doing it right now, is that you don't even need to worry about that right now. So you can basically use these directly and say, okay, what are the important results? And again, you will have a much more extensive treatment of Fourier transform in 111, which is basically, that's the title of the class, Fourier transform. so that's the entire class. But yes, you're right. There are a lot of nuances here that we are just skipping over. Yes?
I'm slightly confused how you found the area of sine 2 pi over 2 pi over t, and then we got that it's like 1 over.
Here? You're confused about the orange part or the blue part?
I think the orange part comes out to be like 1 over a, right?
No, the orange part is 1 over 2a.
Oh, okay.
This thing, it becomes 1 over 2a because this part is pi. This integral, this is pi. That pi cancels this pi. So you're left with 1 over 2a. That cancels this 2a. So the area of this thing is 1. Even before you apply the limit. Even when, not even in the limit. I mean, even just for a finite a, that area is 1. And therefore, for any value of a. So that, then in the limit, but the only thing, the area will remain 1. But the only thing the limit does is makes it very, very narrow and very, very tall. Turns it into a true impulse. In fact, actually, it's better probably to define impulse this way than that like pulse thing, because of what you will see later in like in a few minutes. So, but again, had I started with that, you would say, what? Why did you start with this bizarre function? There are also other ways to define it as an, bell-shaped, Gaussian distribution. Any other questions? All right. Now, there's one more thing to think about this. Like, if you look at this Fourier series business, this expression, right? You could also think about it slightly differently. You can say, okay, in the limit, you know that any integral can be written approximately as a sum, right? So what do? The df's becomes just small steps, the steps of jump, the jump steps, right? So instead of thinking about this as a continuum, you can think about it as like small steps in f. And if when you do that, then this becomes f naught, right? The spacing of these things. So you get f naught x of n f naught, the step size, e to the j 2 pi f, or n f naught t, and then you need to sum this for n going from negative infinity to positive infinity. But if you look at this carefully and call this Cn, you will see that this is, again, this reduces to Fourier series. So it subsumes Fourier series, in fact, right? So if you do Fourier transform, you don't need to do Fourier, if you do Fourier transform of a periodic waveform, what happens is that you will get a bunch of impulses. You will get exactly that. And if you do a Fourier transform of a aperiodic signal, then you will get a continuous thing like this. Does it make sense? Okay. Everyone's good? Shall we carry on? So let's look at a couple examples quickly and see if we can learn some meaningful things from them. So let's say your x of f, the capital X of f, the spectrum, is 1. We want to see what is the time domain function that produces this, right? So what we do, we use that inverse Fourier transform, right? So we say, okay, well then x of t is going to be integral from negative infinity to positive infinity of x of f e to the j 2 pi ft df. And this is 1, so I don't need to worry about that. So I'm left with this integral that now we know how to calculate, so I don't need to redo that. So what was this integral? The same integral as this, right? Which is t. So which says that the spectrum, the energy spectrum of delta, is flat. So if we do like some sort of an x of t and capital X of f, if you start with delta of t, then you get 1. Which means that delta has equal amount of energy at all frequencies. It excites all of the natural frequencies by the same amount. You think about it. You remember we had this discussion about why we use delta and things of that. So you excite all of the natural modes, right? You excite everything. So that's fine. But now let me ask you another question. Now let's say, what if x of t is, or let's say x of f is delta. Let's do the x of t is delta. Doesn't matter. So what if x of f is delta of t? So now this is the opposite. This is a little bit different, right? So what if x of f is delta of t? What is so before we do this calculation, let's see what it means. The spectrum of something has only energy at frequency 0. What do you expect that to be? What is the thing that has only energy at 0 frequency and nothing else? What is it? A constant, right? Something that has no variations will have only energy at DC, right? There's no fluctuation. So we already know what the answer is. The answer is 1, and you can easily see that, right? Because what you can do the same thing, x of t, write the same integral, ditto, and then now you have delta of t here. So if it's delta of t, this value only matters at what value of, delta of f. This should be obviously delta of f. Delta of f. So if it's delta of f, it's only value of when f is 0, so this becomes 1. So you have the integral of delta, which is 1. So it says that 1 in DC gives you delta of f in frequency domain. So in time domain, so you can see a delta in time domain in frequency domain is a constant. And a constant in time domain produces a delta in frequency domain. In fact, actually, probably I want to even replace this with a picture like this. So let's do something a little bit different now. Let's do a Fourier transform of something that's finite in length and see what that does. So let's say you start with, let's say you're trying to make something that's band limited in frequency, meaning a signal that has only energy up to a certain frequency. and no energy above that. We call those a band-limited signal. So let's say we want to have something that has a spectrum that looks like that, like a box. So it means that it has equal energy at all frequencies up to this, W over 2, and after that, it has no energy. The question is that what does that look like in time domain? Do you have any thought about what something that has that property looks like? Any guesses? Yes. It would a sinc, right? So that's a guess, and that's yeah. So it's essentially like a signal that has gone through an ideal low-pass filter, right? Essentially, it's an impulse that has gone through an ideal low-pass filter. Because the impulse had equal energy at all frequencies, right? If you put it through an ideal low-pass filter, only this part of the energy would pass through. So it's the impulse response of an ideal, what you will look at is in fact the impulse response of an ideal low-pass filter. And you will see now why you can't make an ideal low-pass filter in a second. So how do we calculate this? Well, again, we are trying to calculate x of t, right? So we use the inverse Fourier transform, which basically says it's the integral from negative infinity to positive infinity of x of f e to the j 2 pi ft df. You're going to be tired of writing this integral. You're going to write it so much. It's like winning. Anyway. So here's the thing. So what is this integral? It's an integral. So obviously this function is 0 outside those limits. And it's going to be e to the j 2 pi ft df. Okay? So now this integral, can we calculate this? You kind of already have. Right? Can we be a little bit lazy and use this? Because when we did that for a, this is the same integral when a is not going to infinity, right? You're good with this, right? Except for the fact that now a is w over 2. So what I need to do is to write that. So it was 2a, so this becomes w. So if you look at that, it was 2a, so 2a is w over 2. And then it becomes w sine of pi wt over pi wt, which you can write as w times sinc of pi wt. So in time domain, it looks like that. And the height is w. This width is going to be what? So this is when w over, so this is 1 over w, and this height is 2 over w. This width is 2 over w. So now what happens if I had actually something that, first of all, look at this. If I start making this wider, a wider band system, or the response of a wider band bandpass filter, what does happen? What happens to here? This becomes narrower, right? So things, and vice versa. If I make this very narrow, what happens to this guy? This starts getting wider and wider and wider. And in the limit, when I make this extremely narrow, this becomes extremely wide, which is this. And the other limit of this being extremely wide, this becoming extremely narrow. So these are limits of that. Now, first of all, I said something earlier, and I want to kind of like ask you the question about it now. Why is it that you can't have an ideal low-pass filter? What's the problem with that impulse response? Because this would be the impulse response of that ideal low-pass filter, right? Because see, this is a perfect filter, right? This is the all-pass filter. Its impulse response is an impulse. It just doesn't do anything to it. So, Will?
It's not causal.
It's not causal, right. Why is it not causal? Correct, that's correct.
Because
There's stuff happening before the impulse comes in. So it somehow knows what's going to happen before it happens. So it violates causality. So if you don't have a causal system, you can actually create non-causal system in signal processing and all those things. But again, it means that you're doing something that's not physical, but you can do mathematical things that work. You can make that, but the problem is causality. And this is symmetrical. My drawing is kind of bad. So anyway. So does it mean that it's hopeless to make a filter that has not maybe exactly that, but something very similar to that? Yes, continue.
When you made a filter like that, would you have a time delay on the signal?
Yeah, if you had a time delay, right? So if you allow for a time delay, if you let this be shifted here, now Sinc never goes to 0. It kind of like diminishes, but it doesn't really quite go to 0. So at some point you may say, I can truncate it. And instead of this, for example, have a system whose impulse response looks like this. And this would then produce a filter whose frequency response or pass band wouldn't exactly look like that. It would kind of look like this. And the longer you're willing to wait, the more ideal you can make this. And you can see that later on, you will see, depending on what courses you take, that there is this fundamental trade-off between delay and control of the bandwidth, which is essentially the same trade-off that you have in the power in a car, in an internal combustion engine. If you want power, you really need to wait for it. You may have heard the expression of turbo lag. I don't know if you've driven a turbo car, but what happens is that you slam the accelerator and nothing happens. Well, what's happening? And then a second later, you're thrown back. So this goes to something even more fundamental and deeper at some level, which again, we are not going to get into. Okay, so that's for that. And then let's do one more thing. So let's do the opposite. What if my time domain signal is a rectangular shape? Right? What's the frequency domain of that? Do I need to even do that? Well, let's do it for sake of completion. But you probably should be able to guess what it is. So what is this? What do you think the Fourier transform of this thing looks like? The Sinc, right? Because you saw that the good thing about Fourier transform is that it's the inverse is itself, essentially. Again, with that negative sign. But you can do the same thing. You can say, OK, I want to calculate the x of f. So it's the integral from negative infinity to positive infinity of x of t e to the negative j2 pi ft dt this time. Again, the limits of integration become negative w over 2 and w over 2 e to the negative j2 pi ft dt. And when you calculate this integral, you will see it's going to be t sine of pi tf over pi tf. You can write this t sinc of pi tf. The reason some people define sinc as sine of pi x over pi x is that they want to get rid of these pi's that constantly appear here. So in their notation, you will see sinc of tf. Yes?
Should that be from negative t over 2 to t over 2 rather than w?
Yes. I copied too much. So one time I had a friend who's, when I was in college, so he was copying from somebody else's problems, that's right. So what he did, he was kind of like not even paying any attention. So he was like writing something, and then I was actually reading the TA, so I was looking at this. I said, well, this doesn't make any sense. Where does this extra term in this integral come from? It turned out it was actually the lower limit of an integral on the upper line that has kind of like somehow ended up here in the copying process. These things happen. Okay, so what does this tell you? If you think about this, let's just do this. And then the morale of the story is something interesting. So this is, it would be 1 over t and t. Yes?
Is, in general, the inverse of a Fourier transform the same as the Fourier transform if it's symmetric around the y, which is x axis?
Yeah, I mean, so you're saying that the inverse and the Fourier are the same. That's one. Yeah, that's a good observation. That's one observation. That's great. Now, what else can you say? Can you say something about width of the Fourier transform, width of the signal in one domain versus the other? You can see that some things that are narrow in one domain are wide in the other domain, and things that are wide in the other domain, they are narrow in the other domain. This duality of time and frequency is there. In fact, this is exactly, this is not similar, this is exactly the uncertainty principle in physics. Because if you think about it, delta E, delta T is the easier one to explain here. Think about it. Delta T is the width of stuff in time, right? Delta E, what is E? What's the energy of a photon? HF or h nu, right? So it's proportional to that. So when you make something narrow, frequency corresponds to energy, physics, right? When you make it narrow in time, it becomes broad in frequency. If you make it broad in frequency, it becomes narrow in time. Or vice versa, right? So this is the uncertainty principle. That is where it comes from. It's another way of seeing it. Okay. Okay, let's take a quick break, and we'll talk about some applications of Fourier transform, some conclusions.